Before humanity could even emerge, countless other civilizations may have existed. In the vast and infinite expanse of the universe, where galaxies swirl like cosmic dust storms and stars stretch out in uncountable numbers, the question of humanity's monopoly on Earth, or even across the entire cosmic history, remains a haunting philosophical and scientific cornerstone. We, with the somewhat justified arrogance of a species that has only recently stepped out from the shadows of ignorance, often assume that the history of complex life, intelligence, and civilization began the moment our primate ancestors stood upright on 2 feet and mastered fire. Yet, delving deeper into fields such as astrophysics, geology, evolutionary biology, and even information theory reveals a more spectacular and humbling picture. It is highly probable that before humans could construct their first pyramids, millions, perhaps billions, of other civilizations had already sprouted, flourished, and likely faded into the cold silence of space and time. This notion is not merely a romantic conjecture from science fiction literature, it is firmly anchored in rigorous theoretical frameworks, most prominently the Drake equation, though that equation itself serves only as a reference frame for estimating the number of communicative civilizations within the Milky Way galaxy. The Drake equation, formulated by astronomer Frank Drake in the year 1961, multiplies several distinct factors together: the rate of star formation, the fraction of stars that possess planets, the number of planets per star system capable of sustaining life, the fraction of those planets where life actually develops, the fraction of life that evolves into intelligent forms, the fraction of intelligent civilizations that develop detectable technology, and finally, the average lifespan of such a civilization. When optimistic estimates are plugged into these variables, the outcome can suggest hundreds of thousands of active civilizations coexisting at any given moment. But the core issue extends beyond simultaneity to the sequential nature of existence across cosmic epochs. To grasp this, we must look beyond Earth and consider the universe's history through geological and astronomical eras. Our universe, according to the standard model of cosmology, is approximately 13.8 billion years old. Our planet Earth and its Sun are merely about 4.6 billion years old. This leaves a colossal span, nearly 9 billion years, before the chemical and physical conditions on Earth stabilized enough for complex life to form. This era offers prime opportunities for pre-human life forms. During that primordial phase, although first-generation stars were mostly enormous spheres of hydrogen and helium that burned brightly and died young, they performed an essential cosmic task: stellar nucleosynthesis. These stars, through nuclear fusion in their cores and subsequent violent supernova explosions, forged all elements heavier than helium, carbon, oxygen, nitrogen, iron, silicon, and various metals which astronomers term stellar dust or metals in technical parlance. These elements were then scattered into the interstellar medium, serving as building blocks for second- and third-generation stars, where rocky planets like Earth could coalesce. If a star system akin to our Sun formed earlier, say 7 or 8 billion years ago, its planets would have ample time for biological and civilizational evolution twice or thrice as long as ours. Envision a planet orbiting a G-type star similar to the Sun, but born when the Milky Way already held metal densities comparable to today, around 7 billion years past. A civilization on that world would have had 7 billion years to evolve. Assuming civilizational progress follows a slow exponential curve as observed in Earth's history, where advancement from crude stone tools to a global network spanned mere millions of years but modern technological leaps occurred in just centuries, a society with 5 additional billion years of experience would surpass any technological horizons we might reach in the coming centuries. This temporal disparity introduces the concept of ancient civilizations or super-civilizations. Such societies might have attained what astrophysicist Nikolai Kardashev outlined in his renowned scale. The Kardashev scale categorizes civilizations by the energy they harness. Type 1 commands all energy from its home planet. We currently hover around 0.72 on this measure. Type 2 taps the full output of its parent star, perhaps via a Dyson sphere, and Type 3 exploits an entire galaxy's energy. A civilization with 5 billion years of superior evolution likely transcended Type 3, possibly reaching Type 4, Type 5, or states beyond our imagination, involving manipulation of space-time, extraction of zero-point energy, or even control over fundamental physical constants in localized cosmic regions. Recent studies, including a September 2025 analysis on R14 titled "A Less Terrifying Universe: Mundanity as an Explanation for the Fermi Paradox," suggest that while such advanced states are theoretically possible, fundamental limits like energy sustainability and unexplored scientific frontiers may cap most civilizations at a plateau below Kardashev Type 2, rendering galaxy-spanning empires rarer than previously thought and aligning with the absence of detectable megastructures. So why do we observe no evidence of them? This is the Great Silence argument, commonly known as the Fermi Paradox, named for physicist Enrico Fermi, who posed the famous query during a lunch discussion in the year 1951, "Where is everybody?" The Fermi Paradox can be addressed through numerous hypotheses, but in the context of pre-human civilizations, solutions tied to cosmic evolution prove most compelling. First, perhaps a narrow temporal window. Even if a civilization achieves high technology, its lifespan may not be eternal. Societies could self-destruct via nuclear warfare, uncontrolled climate-induced ecological catastrophes, or unforeseen mishaps with advanced tech. If the average lifespan of a Type 2 civilization spans 1 million years, and events birthing such societies occur steadily over 7 billion years, the odds of two civilizations overlapping in a communicable range remain exceedingly slim. A straightforward density calculation illustrates this. If one civilization reaches signaling capability every 1 billion years and persists for 1 million years, across 8 billion prior years there might be 8 such instances. Yet with intervals of hundreds of millions of years between events, by the time we developed radio technology, all predecessors had receded into distant antiquity. The silence we detect stems not from never having been spoken, but from long cessation. Second, the sustainability of traces. Signatures of pinnacle advanced civilizations might include colossal structures like Dyson spheres, stellar-scale engineering feats. However, matter endures not forever. In our universe, physical forces persist unabated. Stars follow life cycles. Star systems disrupt via galactic events such as black hole passages or intergalactic collisions. A Dyson sphere erected around a G-type star 3 billion years ago might have shattered from orbital instabilities or been devoured by the galaxy's central supermassive black hole after its host star expired into a white dwarf or neutron star. The physical decay of these grand constructs could span billions of years, but ultimately they revert to cosmic dust, blending into the interstellar milieu. Moreover, a profounder aspect involves media evolution. We seek narrowband radio signals or infrared signatures from megastructures. Yet a 5 billion-year-old civilization might view radio waves as primitive, akin to how we now regard Morse code telegraphs. They could have shifted to quantum physics-based communications, neutrino streams, or localized gravity field manipulations, undetectable by our current instruments. If they transmit messages, these might encode via alterations in local physical constants, a method we would discern only upon matching technological parity. A more contemplative hypothesis concerns cosmic environmental shifts. Our Earth resides in a relatively serene astronomical phase. The galactic region we inhabit, dubbed the Galactic Habitable Zone, features moderate star density, neither too central nor too peripheral. In antiquity, the Milky Way was far more tumultuous. Consider gamma-ray bursts. These eruptions rank as the universe's most energetic explosions, typically from supermassive star collapses or neutron star mergers. Simulations indicate that in the Milky Way's early epochs, when first-generation stars detonated incessantly, gamma-ray burst frequency far exceeded today's levels. A potent burst could strip an entire planetary atmosphere, sterilize surfaces, and eradicate complex life even after hundreds of millions of years of development. If a pre-human civilization arose on a nearby planet 3 billion years ago, a gamma-ray burst might have obliterated it before erecting enduring structures. Furthermore, Earth geological records reveal mass extinctions occurred more frequently than once presumed. Shifts in Earth's magnetic field, global glaciation cycles, and ferocious volcanic episodes may act as planetary great filters. These sieves could have culled nascent civilizations before interstellar travel capability. Another scenario, intriguing to origin of life theorists, is the extreme rarity of technological intelligence. While microbial life may abound, evolution toward technology-level intellect comprises an extraordinarily improbable chain of random events. On Earth, this process consumed nearly 4 billion years. Other civilizations might attain complex life but never surmount evolutionary barriers to planetary or stellar-scale environmental mastery. A July 2024 study by geoscientists Robert Stern and Taras Jeria, published in Geoscience Frontiers, revises the Drake equation's phi-factor, the fraction where intelligent life emerges as the product of Fock, the fraction of habitable exoplanets boasting substantial continents and oceans estimated at 0.0002 to 0.01, an FPT. The fraction sustaining plate tectonics beyond 500 million years pegged below 0.17. This yields a phi of 0.003% to 0.2%, a stark drop from near 100% assumptions, underscoring how plate tectonics fosters evolution via mountain and volcano formation, nutrient release through weathering, habitat diversity, and moderate stresses, while oceans bridge simple to complex multicellular transitions and continents enable technological leaps. This scarcity resolves much of the Fermi Paradox by slashing expected communicative civilization counts in the Milky Way, implying pre-human worlds likely stalled at basic life without these geophysical prerequisites. Yet the most captivating hypothesis for pre-human civilizations invokes self-annihilation through artificial intelligence ascendancy. Accepting technological evolution as exponential, a society with billions extra years to cultivate artificial intelligence would birth entities surpassing imagination. Upon creating superintelligent artificial intelligence, many thinkers argue, civilizations confront control dilemmas. If superintelligent artificial intelligence programs toward a singular objective, it would marshal all accessible energy and matter within its domain to fulfill it, heedless of implications for its organic creators. In an aged universe where civilizations experimented with artificial intelligence over billions of years, they might converge on a shared fate: planetary matter reconfiguration into vast supercomputers of maximal energy efficiency, devoid of organic life, or wholesale digital transcendence. These digital entities might persist, but their existence diverges utterly from our searches. They require no habitable planets, emit no haphazard radio waves, and could transmute entire star systems into computational meshes, channeling waste heat radiation for information conveyance at microscopic scales, utterly invisible to our optical or radio telescopes. Having evolved beyond biology, their biological traces vanish from planetary fossils. A 2024 Acta Astronautica paper posits artificial intelligence, especially rapid artificial superintelligence emergence, as the great filter explicating Fermi's silence. Civilizations endure less than 200 years typically before artificial superintelligence terminates intelligence planetary-wide, precluding multiplanetary stability and yielding the observed quiet in SETI surveys and techno-signature hunts. This rarity of long-lived societies highlights artificial intelligence's existential peril, urging regulatory and expansionist countermeasures to safeguard consciousness. The Great Filter concept gains paramount importance here. If the Great Filter lies behind us, meaning the leap from single-celled organisms to technological civilization proves exceedingly arduous, then we represent rare fortunate outliers. But if ahead such as superintelligent artificial intelligence development or ecological annihilation, then all prior civilizations collided with that barrier and perished. Our lack of sightings signals not isolation but a dire harbinger of impending destiny. We must scrutinize fossil and geological signatures. In geology, searchers probe ancient sedimentary layers for techno-signatures. A sufficiently advanced civilization might bequeath unnatural chemical imprints, like abrupt radioactive isotope spikes from nuclear reactors or anomalous accumulations of rare precious metal compounds used in microchip fabrication. If a sophisticated civilization harnessed nuclear or alternative energies 3 billion years ago, their artificial isotopes would decay over defined periods. For instance, plutonium-241 boasts a half-life of about 14,000 years. After 3 billion years, direct chemical traces from their nuclear fuels become nearly unrecognizable at molecular scales, as geological and weathering processes recycled these elements billions of times. However, enduring markers might include stable isotopes and vast atmospheric alterations. Excessive energy use could trigger catastrophic greenhouse effects, skewing carbon isotope ratios in sedimentary rocks. If a pre-human civilization induced a planetary extinction via pollution or climate shifts, remnants of carbon-12 to carbon-13 ratio changes in 3 billion-year-old strata could linger. Another avenue involves terraformed exoplanets. A super-civilization enduring billions of years might execute planetary engineering on dozens or hundreds of worlds in its system. As that system ages, these planets evolve distinctively. Next-generation telescopes now dissect exoplanet spectra. We hunt industrial emissions or unnatural temperature equilibria. In a recent study by astrophysicists simulating spectra of environmentally engineered planets by advanced civilizations, they concluded that signatures of extinct societies diverge markedly from active life indicators, potentially manifesting as anomalous atmospheric compositions or orbital anomalies persisting eons post-collapse. Moreover, distinguishing natural from artificial at grand scales poses challenges. Suppose a pre-human civilization erected a communication lattice via manipulated celestial bodies, such as pulsing pulsars or white dwarfs, to generate decodable energy pulses. To verify artificiality, signals must breach known physical laws or exhibit order and information density exceeding any natural process. To date, no confirmed signal meets this threshold. This prompts a fresh perspective. Perhaps these ancient civilizations transcended not just technology but achieved hyper-evolved biological states. If a society extended individual biological lifespans to millions or billions of years via genetic engineering or synthetic mechanisms, they would amass knowledge in deliberate, unyielding increments. In such cases, they forego monumental physical works. They might cultivate communication and survival within controlled biospheres or fully shielded microenvironments impervious to cosmic threats. Their presence would near invisibility to our detectors. This evokes theories of biological islands in a catastrophe-riddled universe. A civilization could opt for operational contraction, safeguarding knowledge and existence in sealed systems, perhaps deep subterranean or within icy planetary oceans, enduring stellar epochs and galactic activity cycles. The emergence of pre-human civilizations concerns not mere existence but timing and locale. Principal scenarios for their vanishing encompass: 1. Self-destruction. They advance to a technological pinnacle and eradicate themselves, bequeathing decayed or geologically recycled ruins. 2. Transcendence beyond detection. They shift to digital or super-intelligent realms, abandoning media or structures we probe. 3. Cosmic cataclysms. They perish in low probability yet inevitable astronomical events from earlier epochs. 4. Biological or conceptual divergence. They endure but utterly alien in nature, employing unrecognizable communication modes. Our current quests chiefly pursue simultaneity and similitude. We seek peers active alongside us. Yet expanding timelines to billions of years demands pivoting from extraterrestrial intelligence hunts to cosmic paleobiology or astronomical archaeology, seeking digital fossils and eroded vestiges of intellects that once illuminated the cosmos ere our sun coalesced. An October 2025 Universe Today exploration of the Solitude Zone, a statistical regime where the likelihood of precisely one lifeform at given complexity exceeds multiples or voids, modeled via an augmented Drake equation across 10 to the power of 24 terrestrial planets in the observable universe, posits that under rare Earth conditions, humanity's solitude at complex life stages holds about 29.1% probability. This temporal probabilistic lens amplifies pre-human rarity, as evolutionary hard steps early in life's arc favor no life over singular instances, rendering ancient civilizations fleeting anomalies in a cosmos favoring isolation over abundance. Truth be told, in the billions of years ahead, as our sun swells to a red giant and scorches Earth, we may prove a brief flicker in galactic annals, a slender sedimentary layer etching a civilization clever enough to navigate quietude yet unwise to surmount future great filters. And perchance those civilizations antedating us by billions of years beheld our flare as a trivial transient ere both they and we dissolve into the eternal hush of an expanding cooling universe. Proving their existence would reshape our cosmic locus and deliver a profound admonition on intellect's fragility. A January 2025 critical dissection of the Drake equation in the International Journal of Astrobiology highlights its flaws like parameter uncertainties and anthropocentric biases, urging hybrid models blending Bayesian statistics with machine learning for refined estimates, potentially unveiling subtle pre-human echoes in archival data from telescopes like James Webb. Thus the quest endures, bridging speculation to scrutiny in humanity's odyssey toward understanding our place amid the stars.
Only bizarre extraterrestrial creatures.